Almost all machine learning models expect neat, perfectly symmetrical information. But when you look closely at raw, real-world data, it is often hopelessly deformed. Look at this split-screen visualization. On the right, you see the perfect bell curve algorithms crave. On the left is actual human data, like income levels or extreme measurement errors, skewing heavily to the right. The machine struggles to process these unpredictable extremes. There is a specific mathematical process to fix this structural mismatch, but if you apply this tool to the wrong type of algorithm, your predictions will completely fail. For many of these systems, the predictive power of your data is locked behind its distribution. If the shape of the data doesn't align with the model's internal assumptions, the underlying signal can get lost in the noise. Algorithms like linear regression and logistic regression operate strictly on a normal distribution. They require those beautiful, symmetrical curves to function. These specific systems rely on normality assumptions. Without a balanced data shape, their internal math becomes less efficient, making it difficult for the model to clearly identify the underlying patterns. Feed a skewed structure into one of these rigid models, and the real-world consequences are immediate. A finance model will fail to accurately predict the exponential property values in a booming real estate market, and a healthcare algorithm will miss the subtle biological markers that signal severe disease risk. You cannot change the rigid mathematical rules governing linear logic. To prevent complete failure, data scientists have to manually reshape the incoming numbers before the machine ever sees them. We fix these structural defects using parametric power transformations. This graph shows that transformation in action. Think of your data as a crumpled shirt and the algorithm as a hot iron. The process stretches and squeezes the underlying distribution, pressing the jagged extremes horizontally until it forces the numbers into a smooth bell curve. This process is driven by a mathematical exponent applied to every number, called the lambda parameter. Finding the exact right stretch is handled completely automatically. The system relies on maximum likelihood estimation, testing multiple lambda values behind the scenes, and maximizing a log likelihood function to calculate the best fit. This automated mathematical search bridges the gap. It acts as the necessary translation layer, converting chaotic human reality into a symmetrical format that machine logic can easily digest. The original tool for this job was developed by George Box and David Cox in 1964. The Box-Cox transformation successfully converted highly skeeved distributions into approximate normal distributions. But the classic Box-Cox formula has a massive mathematical flaw. It relies on logarithms and fractional power calculations. Because you cannot take the logarithm of a negative number, the entire pipeline crashes instantly if your dataset contains zeros or negative values. For decades, data scientists dealt with this using a highly error-prone workaround. They manually added a small constant to shift every single value in their dataset above zero just to avoid the math crashing. In the year 2000, statistics provided an upgrade. The Yeo-Johnson transformation arrived, specifically designed to solve the limitation in the original Box-Cox method. Yeo-Johnson eliminates the need for manual shifting. The formula adapts its mathematical path based on the input sign, routing negative numbers through a different equation so they flow naturally through the system. Because it handles strictly positive data, it processes pure zeros and mixed sign arrays automatically. Yeo-Johnson is now the standard default for data science pipelines. This brings us to a common statistical myth. Many beginners believe they need to iron every single feature in their dataset, blindly applying complex math to every column they have. But tree-based models like Random Forest and XGBoost do not care about normality at all. They ignore your data's shape entirely. Here is a visualization of how decision trees actually learn. Notice how the vertical threshold line slides left and right, making simple splits. These splits are based purely on the numerical order of the data points, regardless of the overall geometric distribution. This establishes a clear rule for data transformation. Reshaping data for scale invariant algorithms like random forests wastes computing power and ruins your model's interpretability. These mathematical shifts are specifically required for the rigid constraints of linear models. We are moving toward a future of highly dynamic, self-healing machine learning pipelines that can sense bad data shapes completely automatically. Soon, these modern systems will deploy Lambda transformations instantly without human intervention, stabilizing variants on the fly. Most practitioners treat these Python libraries as black box functions. By understanding the delicate mechanics of the hidden math, you gain a significant technical advantage in how you prepare your features. Mastering these power transformations allows you to systematically turn the extreme messiness of reality into clear,